Hello, Algebra 2, and welcome to 9.6, Modeling with Trig Functions. This is the last section in Chapter 9 that we'll be doing, and as you know, modeling means story problems. So I hope that you're excited about that. The trig story problems are actually quite a lot of fun, I think, and so I hope that you'll enjoy them as well. Trig functions can be used to model all kinds of problems. Number one, the piston movement in your car, which I put this nice little graphic for you because I don't know much about cars, but I actually went with my family to Cosine, which is the Columbus Science and Industry, Columbus Museum of Science and Industry. And they had a giant piston and it had some, showed us how it works. So what happens is, the cylinder and the combustion happen and they make the pistons go up and down, and then as the pistons go up and down it turns the crankshaft, and then that makes your car go. So there you go, that's my explanation for that. The circular motion of a Ferris wheel, the pressure of a single frequency of sound, and yearly temperature data, and there's lots of more things that can also be represented with sine and cosine functions. So that's what we're going to be looking at today. Before we do that, I want to make sure that you know the vocabulary words of period and frequency and how they relate to each other. So period in general, if we think about the sine or cosine curve that we did last section, or in 9.4 actually, the period is the amount of time on the x-axis that it would take for one complete cycle to occur. So if we think about the period as the time per one complete cycle, and that's regardless of what the units happen to be, right? So in this example, if one trip around the sun of the earth is 365.25 days, then the amount of time would be 365.25 days per one trip around the sun, right? Or for 1 year. And normally we don't like mixing decimals and fractions or having compound fractions, but it's really important for the number that we get for the period that it's not a fraction. So we actually prefer, even if this happens to be a decimal, that's okay. We just leave it that way because we want 1 on the denominator. Turns out, so the definition of frequency would be the number of cycles per unit of time. So for the same example, we want 1 unit of time here on the bottom. Well, if we know that one trip around the sun is 365.25 days, I can say, well, so one cycle or 1 year every 365.25 days, and then now I'm going to need to actually divide those because I need a 1 on the denominator. So in my calculator, I'm going to hit 1 divided by 365.25, and that says that that would be equivalent to 0.00273785, etc. of a year per 1 day. And so how are period and frequency related, you ask? I'm so glad you asked. Period and frequency, if we look at this, this is time per cycle, and this is cycles per time. So how are they related? They're reciprocals. Period and frequency are reciprocals of each other. That tells us a lot about then how we can work with frequency in story problems as well. We know that the period is 2 pi divided by b, right? Whatever the b value in the equation is. So if period for a sine or cosine is 2 pi over b, then that means that the frequency would be the reciprocal of that, and that would be b divided by 2 pi. We can also solve both of these equations for b if that's what we're given. So in this case, b, if I use the flip-flop method, b would be 2 pi divided by the period. But if I have frequency given to me and I want to find B, if I solve this equation for B, it's already on the numerator. So all I would need to do is multiply both sides by 2 pi, and I would get that B equals 2 pi times the frequency. So hopefully you understand a little bit more about frequency and period now. Some of the examples that you would need to do just give you an equation and they say find the frequency. So you know the B value in each case, and so you would find the frequency. For instance, I'll do this first one for you. In the first one, the B value is 1. And I know from hopefully the notes that you're taking that frequency is B divided by 2 pi. So the frequency would be 1 divided by 2 pi would be the exact frequency. And then if we wanted to get a decimal for that, we would just divide 1 by 2 pi and make sure that you would type the 2 pi in parentheses in your calculator. Go ahead and try the other two. Pause the video while you do that. And then we'll resume in 3, 2, 1, 0. Check your answers. For this one, it would just be B over 2 pi. So 5 over 2 pi, and there's not much you can do with that. However, in the third example, you'd have pi over 2 divided by 2 pi, which is pi over 2 times the reciprocal, which is 1 over 2 pi. And the pi's would go away, and we would end up with a frequency of 1/4 for the third equation. So hopefully that made sense, and we'll just move right along. So the next kind of example that you'll see in the book is for pressure of a sound. And so we're going to use the following template. This is like your formula template, and then that should make the problem super easy. The pressure at any given moment is going to be the maximum pressure of the sound, which would be that height of your amplitude, times sine of 2 pi times the frequency times x. So for your example, the lowest frequency that humans can hear is 20 hertz with a maximum pressure of 0.02 millipascals. So we would go ahead and write the pressure at any time would be 0.02 times sine of 2 pi times the frequency, and that frequency is 20 hertz, times x. Or we could use t for time if we wanted. So we would end up in this case with 0.02 sine of 40 pi x would be the equation to represent the pressure at any time x. We could also use a cosine function here because no starting value was given. And remember that sine and cosine functions look the same except for just a shift. But generally the default is that we would use a sine function if we have the choice, if it doesn't say which one, or if it doesn't matter to us which one we would use, we would pick sine. And then the next example is a circular motion example. So you go to the fair and you ride the Ferris wheel. The Ferris wheel bottom is 5 feet off the ground, and the wheel has a diameter of 50 feet. It makes a complete turn every 3 minutes. Model this with an equation. So to set this up, let's think about what would happen. So I'm going to just draw a little picture here. This is the ground. It says that the bottom of the wheel is 5 feet off the ground. So if you're going to start on the Ferris wheel, let's just say that here's the bottom. So we'll put the bottom on there. And then what would your height look like as you travel along the Ferris wheel? Well, you would go up to the top, and then you'd go down, and then you go up, and then you go down, and hey, look at that. It looks like a sinusoid. So if we put some numbers in here, we said that the bottom of the wheel here is 5 feet off of the ground. And then if the Ferris wheel diameter is 50 feet, that means this entire range from top to bottom would have to be 50 feet, which means that the amplitude would have to be half of that. So the amplitude would be 25 there. And you could mark it on the bottom half as well, that would be 25 feet. That would take the maximum to being 55 feet above the ground because the bottom of the Ferris wheel was 5 feet above the ground. Also, then we would need to figure out the midline here. So we can figure that out by saying, well, the bottom is 5 feet above the ground, and then it's 25 feet to get to the midline. So this midline must be at 30 feet. Using that, we can now say y equals, or h equals for height if you want, the amplitude, which we know is 25, times the sine or cosine, it doesn't matter. We can put the y-axis here wherever we want. It doesn't tell us. So I'm just going to put the y-axis like, I'll just smack it right there. And then that makes this a sine curve because it's going to start at the principal axis on its way up. So it makes it a sine curve. And I'm not quite sure. I'm going to need to adjust for the period. So I'm not quite sure what that is. I haven't done that yet. I'm going to leave that blank. And then the principal axis, or the midline, would be 30 units above the ground. So this would be my answer, except for I need the b value, and I can get that from the period. So if it makes a complete turn every 3 minutes, that would be the time per 1 cycle. So that's the period. It's not the frequency, right? And so if 3 minutes is the cycle, and that's 2 pi divided by b, then the flip-flop method tells us that b would be 2 pi divided by 3. And so then my end equation would be y equals 25 times the sine of 2 pi thirds x plus 30. You could check that in your graphing calculator. Just make sure in your calculator, if you're working with radians, anytime you see pi in there, then it means you're working with radians and you would need to be on radian mode. Okay, 2 left. Temperature data is one that we actually do need a calculator for. So if you're trying to follow along and make sure that you're testing it in your calculator to get the same answers, make sure you have a graphing calculator on you. If you don't have your graphing calculator on you for some reason, there are applets online that will do the same. And so you can always type in graphing calculator applet, but I would recommend that you just use your own graphing calculator if you have that. So yearly temperature data, if we look, we have here, this is for Houston. We have in Celsius, the average maximum temperature for each month and the average minimum temperature for each month. And you can see if I would put them together, that it's going to be modeled by a sinusoid graph because it goes up in the summer, down in the winter, right, every year. So if we want to use this data to model the average monthly high temperature for Houston, then we're going to have to enter that data into our calculator. And so hopefully you know how to enter that data into your calculator via the list. But if not, I'm going to go ahead and do it for you on here. You can skip ahead if you already know how to do this. So we're going to go ahead and go to the stat button and hit enter for edit. And if you have anything in your list 1 and list 2, you can hit clear, enter, and then go up onto top of list 2 and hit clear, enter to clear out those lists. So in list 1, I want to just put the numbers 1 through 12, which would just represent the months, right? So 1, 2, 3, 4, 5, 9, 10, 11, 12. Okay. And then in L2, I would want to go ahead and put those maximum monthly temperatures. And this one happens to be in Celsius. So we would go ahead and type 18.2, 19, 21.4, 24.4, 27.3, 30, 31.5, 32.1, 30.3. Oh man, I'm typing too fast for this. Let me go back and fix those. Can't handle my typing speed. Okay, 27.5, 23.3, 19.8. Okay, so now we have our data in there in L1 and L2, and we want to model this just like we would find any other regression line throughout the course of the year. So we can go ahead and quit out of that, and we can go to stat and then over to calculate because we want to calculate a regression. And then if you go down until you find the one that says sine reg, which is C on my calculator, and I'm going to hit enter. Iterations means the amount of times it's going to run that cycle through the program to find your equation. Please just leave that on the default of 3. We have our x's in L1 and our y's in L2, that's correct. You'll see the period is here in case you want to tell it what period to use, which is kind of nice. In this case, we know that the period should be every 12 months. So we could type in a period of 12 here, and then we could see what that would give us versus not typing in any period and letting the calculator find the period and telling us what it gives. We're just going to leave it blank, and we're going to see what the calculator tells us it is. Store a regression equation. If we would like to see that stored in Y1, then we could choose to store that regression equation in, no, looks like I'm on parametric mode, so we won't even mess with that. So we could store the regression equation if we wanted to in Y1. We don't really need to get the equation. I just thought it might be nice for you to see. And so we're just going to go on down and hit calculate. And notice now that here's our equation, and it gives it to us without the b value factored out from the c value. So you have to be a little bit careful about that when you go to type in your answer, depending on how Big Ideas might want you to type that in. But we get y equals 5.087 approximately times the sine of 2.423 x without the extra set of parentheses, because we can see that in the calculator that that's what it's giving us, plus, not minus, 1.367. And then our principal axis, our d value would be 23.979. And then once we've grabbed all those numbers, I no longer need to show you my calculator. Then that would be the answer to the problem, as long as that's all at once. So we know that 23.979, which would be about right there, is the principal axis on the graph. That seems to make sense. And the amplitude would be about 5.087, which means from that we're going about 5.087 up, and we're going about 5.087 down to get to the minimum max temperature per month. So there's that one. And then last but not least, just if I give you a graph and I say model this with the sine or cosine function, we should be able to do that just with the 2 little points that I've given you along with this graph. So for this graph, because I've given you a principal, an initial value of 7, and it's starting at the maximum height, then I think that this would be easier to use a cosine function for this one, because it's a cosine function that starts at the top. The sine functions start on the principal axis headed up, so make sure you keep those in mind. So I'm going to use a cosine. We could use a sine if we wanted to, but we just don't. We're going to use a cosine function. And I need to figure out what the period is, and what the amplitude is, and what the principal axis is. So I'm going to look at the max and min values. The max value is 7, and the min value is 3. So that means the range from 3 to 7 is 4 units, and so the amplitude must be half of that. So 7 minus 3, which is the range, divided by 2 is going to be your amplitude. And so then that we can see that the amplitude would be 2. And the min plus 2 takes us to a y value of 5, or the max minus 2 takes us to a y value of 5. So I can see that the principal axis is 5. I can also get to the principal axis by taking 7 plus 3 and then dividing by 2. And I can get to my d value that way. And now the only thing left that I have to find would be the b value based on the period. So I can see that I've traversed half of a cycle from x equals 0 to x equals 8, which means that a full cycle would be from 0 to 16. So if I know that the period is 16 and I say that 16 is 2 pi divided by b, then that means, via the flip-flop method, that b would be 2 pi over 16, or pi over 8. And so now I have an equation to model this. Just based off of those 2 points, I was able to find the period, the amplitude, and the midline, which were the 3 things that I needed. So I hope this is a fairly complete lesson, and now you'll have super fun doing your 9.6 homework. Enjoy. If you have questions, make sure you come to office hours.